Hmm. Hi, folks. Let's finish this work with our last section of Chapter 9, the dot product. Now, please make sure you watch my previous lecture on Section 9.4, vectors, where we defined vectors. We had a few formulas such as magnitude of the vector, things like that. Real quick, let me flash this. Section 9.4, vectors, we defined the vectors. We looked at vector addition, vector subtraction, scalar multiplication, properties of vectors, magnitude of the vector, and so things like that. Again, please make sure you review the previous section if you need some of the reminders of what we're going to do today. All right, so what are we going to talk about? This time, we're going to talk about the dot product. Now, we talked about vector addition, vector subtraction, and scalar multiplication by a vector. What we haven't done yet is vector multiplication. So in a way, that's kind of what we're doing today. Okay, so suppose I have two vectors here. I'm going to label them as u and as v. Okay, and suppose the angle between them is theta. Now, most textbooks, by the way, they go right away and give you the dot product, which is also known as a scalar or inner product. Scalar. And it's also known as the inner product. And before I do that, I just like to motivate this a little bit, just so it's not just a formula thrown at you. Now, when it comes to these two vectors u and v, let's do the vector u minus v. Okay, so how do we do u minus v? Remember, this is vector u, and this was vector v. Okay, now vector minus v is same magnitude as v, only different in direction, right? We just changed the direction. So that's going to be the vector negative of v. Okay, there it is. Now, we're doing u minus v, so to subtract v from u minus v, we actually add the negative vector v to u. Okay, so in other words, we're adding two vectors, and if you remember, the way to add vectors, we used a couple of methods earlier. Again, that was in the previous lecture. We used the tip to tail method. So we go from tip of one to the tail of the other. See that? That's tip to tail. Tip of one to the tail of the other. So if I go from tip to tail, then that means this is going to be, the blue vector is going to be the difference vector. Yeah? That's u minus v. Okay, so I'm just going to transfer this onto my graph up here. And there you have it. So u minus v actually extends from the tip of v to, that would be the initial point, the terminal point would be the tip of u. And there we have it. So far, no mention of dot products. Okay, now at this point, let's say I want to find the magnitude of that difference vector u minus v. So to do this, we're going to use the law of cosines, right? And if you recall, the law of cosine help us solve the case where we have side, angle, side, right? We have two sides in a triangle and an included angle. Well, the two sides of this triangle are u and v. The included angle is theta. Therefore, I can do magnitude of u minus v. Now, by law of cosines, the square of one side is equal to the sum of the squares of the other two sides, negative twice their product of the magnitude of the vectors in this case, times the cosine of included angle, in this case theta. All right, now I'm going to assume that vector v has components in the form ai plus bj, which we can also write it in algebraic form ab, and vector u. And by the way, vector u here, I know before I used it for the unit vector, this is a general vector now. It's just another vector. I guess it could still be a unit vector, after all, is a vector. So it's not necessarily, though, a unit vector. You see that it has components C and D. Okay, now how do I find the magnitude of these? Well, the magnitude of u minus v, let's take a look at that one first. Let's do vector u minus v. So I'm trying to do the left side first. Okay, that's what I'm doing. So magnitude of u minus v, well, u minus v, let me actually do that. Let's find this vector u minus v. So u minus v is going to be, remember, u is CD minus v is AB. So we subtract the first components, that's C minus A, subtract the second components, D minus B, and that's how we get u minus v. Now, what is the magnitude of u minus v squared? That's when you do C minus A, right? You square each component and take the square root of. That'll give you just the magnitude. But then keep in mind, we're squaring that also. So the result is to get rid of the radical. I'm going to expand the binomial under the radical sign. So I get c squared negative 2ac plus a squared. And then I get d squared negative 2bd and then b squared. Okay, so I got those 6 terms. And that's what magnitude of u minus v squared is. And that's the left side. Okay, so we're just going to leave this for now. Okay, so we have that. Now, let's focus on the right side. And actually, I'm going to write both left, right side together now. Okay, so the left side we just showed, the left side is going to be c squared negative 2ac plus a squared plus d squared negative 2bd plus b squared, right? Equal to, now I'm working on the right side here. The right side is magnitude of v. Magnitude of vector v, that's going to be square root of a squared plus b squared. And then you get square it plus, again, I just did that part. And then I'm doing what's next to that. That's square root of c squared plus d squared, and then magnitude of that squared. Negative twice magnitude of each of those. Well, again, magnitude of u, I'm going to keep it like that. Magnitude of u, magnitude of v, cosine theta. I'm not going to change that expression. Okay, so this part, I just copied it here. All right, now we can actually cancel some things in a moment here. Well, first on the right side, the square root of anything squared gives you the radicand back. So we get a squared plus b squared, and then c squared plus d squared. Negative twice product of the magnitudes of the two vectors and the cosine of included angle. Okay, now what are we going to do next? Well, you look at both sides of the equation. Now I have a squared here. I have a squared on that side. They cancel. B, C, D squared. And I have B, C, D squared. So all those squares go away, right? And what do we have on the left side? Well, I have negative 2ACBD. I'm going to factor negative 2. And that gives me what? AC plus BD. And on the right side, I just have negative 2 magnitude of vector u times magnitude of vector v cosine theta. All right, and the next step, of course, is you can divide by negative 2. And there we have it. So we have AC plus BD is equal to magnitude of u times magnitude of v cosine theta. Now, the expression that's on the left side, this is what the dot product is called. Okay, so we're going to use now the dot product notation. Let u dotted with v, these vectors, be AC plus BD. And in this case, I can write u dot v, that's the left side, equals to the right side. So the motivation for this again is I'm trying to show you some geometric interpretation of what is a dot product. I mean, often you ask people, what is a dot product? And they really don't know because they've never seen this, most likely, this way of defining a dot product. They were just given this formula. Now I'm going to give you the formula that's in the book. U dot v is equal to, and of course, again, vectors u was CD, vector v is AB, and u dot v is product of AC plus BD. And this is all they tell you. That's it. So again, hopefully this will give some motivation for this definition. So the geometric interpretation, therefore, of a dot product is this. The dot product of two vectors is geometrically the magnitude of one vector times magnitude of the other vector multiplied by the cosine of the included angle between them. That is what the dot product is. Okay. Now, having done this, actually, we can write a formula for the angle between two vectors. So let me do that. Anytime you want to find the angle between v and u, in this case, two vectors. Okay, remember we have to use the arrow notation to indicate that these are vector quantities. Now my arrow, by the way, when I write it sometimes, a lot of times it looks like this. Those are the same things. Okay, so please be flexible. The angle between two vectors, well, if we divide both sides by magnitude of u and magnitude of v, remember, those are numbers, right, which we call scalars. So that product is just going to be a scalar, right? Scalar u, scalar v means just a real number. So I can divide both sides by that. Therefore, I have u dotted with v divided by magnitude of u, magnitude of v. And there we have it. You see that? And this will give us the cosine of the angle between them. So how do we find theta? Therefore, theta is the actual angle, right? For theta, we get cosine inverse of that expression of u dotted v divided by magnitude of u, magnitude of v. And if you remember from chapter 7, when we did this way back when, one of the previous lectures, we mentioned the range of inverse cosine, right, is between 0 and pi. So that is why vectors, the angle theta for a vector is often from 0 to pi. It has to do with the range of the inverse cosine. And there you got it. Okay, so this is actually a formula that will find the angle between two vectors. Now, a couple of things to note here. One, the first note is that if theta is pi over 2, that means the measure of the angle is 90 degrees, correct? Right angle. Well, cosine of pi over 2 is 0, isn't it? Is 0, which means if I plug into this formula, I get 0 equals u dot v over magnitude of u, magnitude of v, right? And in order for this fraction to be 0, because u and v are not 0, these are scalars, these are not 0. Okay, so the numerator has to be 0. That means u dot v, which is a scalar multiplication, the inner product, has to be 0. So oftentimes if a question, or if we need to establish that two vectors are orthogonal, that means the angle between them is 90 degrees, we just show that the dot product is 0. Two vectors are orthogonal. Now sometimes they call them normal vectors, perpendicular vectors, and so on. So typically orthogonal is the common vocabulary here. Two vectors are orthogonal if and only if their dot product is 0. This is actually a theorem, and we kind of have proved it just now, part of it. Okay. Now, the other note to make here, that was about orthogonality. What if the measure of angle theta is 0 or pi over 2? Well, if theta is 0, that means cosine theta is 1 now, right? Cosine theta, because cosine of 0 is 1. All right, so in that case, that would mean that the dot product is simply going to be the magnitude of u times the magnitude of v. Okay, that's only if theta is 0. All right, now, and then the two vectors are going to be parallel. I'll tell you a little more about this in a moment. If theta is pi, again, cosine theta is -1 now, because cosine of pi is -1. So that means u dot v is going to be negative magnitude of u, magnitude of v. Okay, so that's what that would mean. Now, in either case, we have what we call parallel vectors. So let me write this. If theta is 0 or pi, then two vectors are parallel. Okay, now, how can two vectors be parallel? Let me show you different ways they can be parallel. For instance, let's say this is vector u. Okay, and then another vector parallel to that is going to be this one. So that would be parallel vectors, right? Call this one v and the other one is u. So those are parallel. Clearly, that's just like parallel lines, right? In this case, they do not form an angle, in fact, right? But remember, we can translate vectors. Like if I have a vector over here, okay, I can bring this vector and place it here, right? Or I can place it at the tip of this vector, right? As long as it has the same magnitude and direction. So that's an equivalent vector. Well, when they're parallel and theta is 0, so they could be in this form, or I can write them like this. And this is going to be vector u, and vector v, I'm actually going to put it alongside in front of that. There you go. And here's a case where theta is 0. The angle between the two vectors is 0. And in fact, one overlays on top of the other, right? We can show the vectors this way. Here's one, and the other one is directly on top of that one. So here you have both u and the vector. And there you go. This would be v. Theta is 0. So they can be parallel and going in this, going like that. Or they could be, what about the case where it's 180 degrees, the angle between them? Let's say this is u. And the vector v actually goes in the other direction. You see that? So here the angle between them is 180 degrees. In either case, these are parallel vectors. And again, you may say, well, how's that parallel, right? Well, it's parallel because I can draw u here, and I can actually move v directly below as an equivalent vector. And there you go. Now they are parallel. You can see. All right. Now, in general, algebraically, let's conclude it with this. We're going to say that two vectors are parallel if you can write one as a scalar multiple of the other. So vector v is alpha. Again, alpha here is a scalar, a number like 2, 5, -1/2, whatever it might be. Okay, and then the two vectors are parallel if one is a constant multiple of the other, in other words. Okay, Now, for instance, let's take a look at an example here. Okay, in this example I want to do, let's do this one. An example. So I'm just making up two vectors. Let's say my vector v is 3i. Let's make that 4j, so they're not the same numbers. And I'm going to make w to be negative 6i minus 8j. And you can kind of see 6 being a multiple of 4, 8 a multiple of, 6 multiple of 3, 8 multiple of 4. So for this one, let's find the dot product, v dot w. Well, v dot w is going to be, that's 3, 4 dotted with negative 6, negative 8. And the dot product, you multiply 3 by negative 6, plus you multiply 4 by negative 8. First component, second components. So this is going to be negative 50. Okay. The fact that dot product is in 0 tells me these two vectors are not orthogonal. Okay, now are they parallel? That remains to be seen. Let's find the angle between them. Well, the angle between, remember cosine theta, we had a formula, is the product, the dot product, inner product, scalar product of the two vectors divided by magnitude of each of those vectors. Okay, well, the dot product, we established it just now. That's negative 50. To find the magnitude of v, you square its components, 3 squared, 4 squared, times. You square the components of w, negative 8 squared. And this is going to be negative 50 divided by square root of 25, that's 5. Next to that, square root of 6 squared, 36, and 64 make 100. Square root of that, 10. And cosine theta is negative 1, right? So theta is arc cosine of negative 1. And in the 0 to pi range, theta is going to be pi. This is a quadrantal angle, right? 180 degrees. Therefore, the fact that pi, the angle between them is pi, tells me that the two, therefore v is parallel to w. They're parallel to each other. So in terms of the definition of parallel vectors, again, remember, I can write one as a constant multiple of the other. And it doesn't matter. You can go w is, I don't know, let's go beta. So it's a different scalar now. There. That's what parallel means. You can write one as a scalar multiple of the other. So now remember, my vector v is 3, 4. Let's find that scalar multiple in this case. And w was negative 6, negative 8, correct? All right, well, the only way this thing can happen, where I have 3 for the first component, I'm going to let alpha be negative 1/2. Negative 1/2 times negative 6 and negative 8 gives you 3, 4. You see that? They're exactly the same. So that's what we mean by one as a multiple of the other. So that's what the scalar is that makes this work. Now, if I go with this version, w, now I'm going to show w can be written as a scalar multiple of v. Well, w was negative 6, negative 8. And how can this be? Well, beta times and vector v at components 3, 4. So this time, if I let beta be negative 2, how's that? Let's let it be negative 2. That's the scalar. You see that? So I can write negative 6, negative 8 as negative 2 times 3, 4. That's clearly the same, right? So notice the scalar changes depending on whether we do a constant multiple of w or constant multiple of v. But however we do it, that's what we mean by these being parallel. Okay, now how can they be parallel? Geometrically, by the way, let me grab my coordinate system here. Okay, here's my coordinate system. So let's graph a vector v first. Suppose this is 1, 2, 3, and then I'm gonna go 1, 2, 3, 4. So this is gonna be that vector, right? Right in here. That's vector v. Okay, this is 3, 4. Vector w is negative 6, 8. So it's gonna be twice the x and twice the y. It's going to be down here, and it's kind of like way down here. Now if I draw this vector, there you have it. This is vector w, negative 6 and negative 8. So you see how they can be parallel. Again, you may say, well, they don't look parallel because you're used to lines being parallel like this or like this or like this. How can these two vectors be parallel? Well, I can draw them like this. All I need to do is keep v the way it is, and I can transfer w and make it go like that. There you go. That's an equivalent vector to w. You see that? So that's why they are parallel. So they could be parallel, literally parallel, like railroad tracks, or as long as one is in the direction of the other one. So when we say vectors are parallel, we talk in that sense. If two vectors are parallel right here, that means v lies along w and vice versa. Okay, that's what we mean by them being parallel. All right, now what about the properties of dot product? Let's take a talk about the properties now of dot products. Okay, now with the properties of dot product, the most common ones, the ones I write them, are the commutative property of dot products. So whether you do u dot v, v dot u, it's the same scalar. Remember, dot product is scalar. The result is a number, not a vector. It's not a vector product. Okay, and then the distributive property says if you do vector u dotted with the sum vector of, let's say, v plus w, then we can write this as u dot v plus u dot w. Okay, so that is commonly known as the distributive property. Okay, and again, I want to emphasize u here is not necessarily the unit vector that we've been talking about. Okay, now another property here. What if I do a dot product of a vector with itself? Well, let's take a look at this. Let's say vector v is ab and dotted with itself. So with AB again, remember, dot product, you multiply first components together, AA, plus multiply second components together, BB. And remember, the magnitude of vector V, we defined it earlier in the previous lecture as the square root of A squared plus B squared. So what you see here is actually magnitude of V squared, isn't it? That equal to magnitude of V squared. Okay, so any vector dotted with itself gives you magnitude of the vector squared. Now the zero vector times any vector, that would be, let's say, in a two-dimensional case where we have only A, B, two components. If I dot these together, I have 0 times A plus 0 times B, and that's 0. Now, I want to emphasize that this 0 is a vector of 0. This is a scalar 0. There are two different things for us, folks. See, doesn't have an arrow on top. So this is like a real number. This is a real number. Whereas 0 vector is a vector whose magnitude is 0 and its direction is any direction you want it to be. You simply have just the tip of an arrow. That's all you have. Okay. Now, let's take a look at this next idea. We're going to talk about sometimes you're interested in projection of a vector onto another vector. So let's talk about that. Okay, what are we going to talk about? We're going to talk about projection of V onto W. One vector onto another. So notationally, by the way, this is how we're going to write it. PROJ, projection of V and subscript W. Subscript W is the one that's being projected onto. Okay. Now, before I actually show you how I'm going to get that formula, let's set this up. For instance, let's say here is my vector W. Okay, and then I'm going to have a vector V like that. That's vector V. And the projection is literally just that. When you project, means you drop a perpendicular from the tip of V onto W. So this is a right angle. Okay, and that will actually provide, there you go, it gives you the horizontal component of vector V. So this is what V horizontal is, and that is indeed the projection of V onto W. Okay, now we can also break down and decompose V into its vertical components. So that's V subscript V for vertical. Okay, and then I can of course transfer this vector over here, and it's going to be exactly the same vector here, equal in magnitude, going in the same direction. Okay, so this is also V vertical. All right, now when we do this, therefore, now check this out. Suppose I have, let's say, V horizontal and V vertical looks like the one I have up here. So I have that. If you look at tail to tip, this vector is going to be the sum vector, right? So that is actually VH plus V vertical, which happens to be the vector V itself, right? Okay, so doing it this way, the way I have, it justifies me writing the following. Therefore, vector V is simply made up of two components, a horizontal and a vertical component. The horizontal component of it is what projects onto W. Okay, so that means, and remember, when it projects onto it, if you look at this now, look at the projection and look at W, they go in the same direction, so they are parallel, aren't they? So I'm just going to say that the horizontal component, right, which is equal to the projection of V onto W, is parallel to W. Again, by parallel here meaning in the same direction of, okay, and parallel to W means it goes in the same direction. All right. So let's see if we can find a formula for the projection. Okay. Now, if I do a dot product of V dotted with W, well, remember V has horizontal vertical components, right? So I'm just going to write it as a horizontal and a vertical component. And then we're going to dot it with W. Okay. Now, using distributive property that I cited earlier, right in here, distributive property, we're going to distribute W to both horizontal vertical components. So it's going to look like this. We're going to have the horizontal component, right, dotted with W plus the vertical component dotted with W. Now go back to the drawing. Look at the vertical component and W. They form a right angle, correct? So the angle between them is 90 degrees. Right, let me just real quick draw it here. This is VV and this is W. See, the angle between them is a right angle. If the angle between two vector is 90 degrees, they are orthogonal. That means the dot product is 0. So that part is 0. So we can say that the dot product of vector V with W is the same as simply the horizontal component of it, right? So that's the takeaway from this. That's simply the horizontal component dotted with W. Okay. Now, because the horizontal component is parallel, right? We just said that here. Because the horizontal component is parallel to W, meaning it's going in the same direction as W. Well, by definition of two parallel vectors, that means I can write a horizontal component as a scalar multiple of W, true? Okay, we established that earlier. So I'm just going to change VH with a scalar multiple of W, right? Dotted there, dotted with W. Now, the scalar is a number that comes outside. The only dot product takes place with vectors. So we go W dotted with itself. Well, just a few minutes ago, we said any vector dotted with itself gives you the magnitude of the vector square, right? So I'm just going to write this as alpha times the magnitude of W squared. And from this, looks like alpha is going to be V dot W divided by magnitude of W squared, right? That's what alpha is. All right, and we're almost done with this. We're going to bring it home. So what is, and right in here, in fact, I'm going to substitute for alpha in here. Therefore, we can say that the horizontal component, remember that is the projection, is given by V dot W over magnitude of W squared. That's the alpha part times vector W. True? There you go. Here's your alpha. Now, what else? Well, that should be it. That's it. So let me give you now, again, the takeaway from this. Projection of any vector onto another vector is therefore given by, right here, because that's what VH is given by this formula. It's going to be V dot W over magnitude of W squared times vector W. And there you have it. Okay, this is the formula you want to know. Now, sometimes we look at just, because remember, projection of V onto W, this is going to be a vector that is in the direction. See, W here, it's in the direction of W. Now, sometimes we're interested in the magnitude of this vector. If you look at the magnitude of the vector, then they call it the component of V onto W. That's simply magnitude of the projection vector. And there you have that one. Okay, so component of V in the direction of W. Now, what would be example of this? For example, this component, oftentimes quantities such as velocity, such as force, things like that, we are interested in their components. Okay, now How do I find the component, which is magnitude of the projection vector? Well, that would be the magnitude of this, right? Of v dot w over magnitude of w squared times w. Now going back to, again, properties of vectors, we can, because remember, this expression, this is a scalar, right? It's a constant, in other words. So the constant, when you do magnitude, you can bring actually the constant outside. So that's v dot w divided by magnitude of w squared. And then just do magnitude of vector w, right? It's kind of like factoring this. You bring this outside. So all you have is magnitude of w. Okay. Now here I can actually simplify this, right? Because I have square of the magnitude on the bottom, magnitude in the numerator, and that actually reduces the formula down to v dot w divided by magnitude of w. All right, and there you have it. So this is the formula for magnitude of the projection vector. That's what the magnitude of the projection vector is. All right. Now let's take a look at an example with projection here. Okay. Let's say I want to find, here's my example. Suppose I'm given two vectors. Suppose vector v is, I'm going to go 3i plus j, and vector w is negative 2i minus j. Okay, and we want to find projection of v onto w. Okay. Oh, and by the way, in your book, this is important. See, I use w, vh and vv, like in here. That makes sense to me because I have horizontal. I'm going to call it h, and vertical, call it v. The book, your book actually calls this v1, v2. Okay, so, so if you use your book or the help functions of the software we're using, you see v1, v2, that's what it is. v1 is the horizontal. Let me write that. v1 is the horizontal component of vector v, and v2 is the vertical component of the vector of v. Okay. And projection of v onto w, again, I call that vh, which your book calls v1. So let's put it all together here so you have it in one statement. Okay. And what is this given by? Remember the formula we had is the dot product over the magnitude of w, the vector that you're projecting onto, and then it's going to be in the direction of w, so you multiply by w. And remember, by the way, projection of v onto w is different. Let me write that. Projection of v onto w does not equal to projection of w onto v. It's a different projection, and maybe with it, in this example I'll show you both. Okay, so first I gotta do v dot w in the numerator. That's when we do 3 times negative 2, right? A, C, and then plus BD is 1 times negative 1. That's the dot product. And in the denominator, magnitude of w, well, w is negative 2 squared plus negative 1 squared, square root of. And then this gets multiplied by w. Well, w in algebraic form is negative 2 comma negative 1, right? You can see how these are all numbers. That's a scalar. And that's what we were saying, that this expression is just a scalar. All right. So what is this going to become? The numerator is negative 7. The denominator is going to be 5, right? Because you have square root of 5. Oh, and in the denominator, by the way, we were squaring it. I forgot to square it. The magnitude is the square root of 5, but then you have to square it, right? So that's going to be negative 7/5, and then we're going to multiply that by vector w. All right, and when we do, now we have the projection. So it's going to be in, again, algebraic form, 14/5, comma, 7/5, which we can write it in the ij form as 14/5 I plus 7/5 j. Okay, and that's what the projection is, V1. Once we have V1, the easiest way to get V2, because remember, the vector V is made up of V1 plus V2, right? Which in my notation, horizontal plus vertical component. Okay, therefore, V vertical, which is V2 in your book, is given by V minus V1. And that's when you do 3,1 minus the one we just found, the projection vector, these, and then what do we get? We're gonna have 1/5, comma, negative 2/5. And this, by the way, will be, this is like a position vector. So if you graph this vector, it's going to start from 0, 0. All right. And that's what this is. Now, let me actually kind of do the geometry of this for you. Okay, I'm going to put the geometry of this on here and then explain it. Okay, so here is the a schematic of what's going on with this example. So I have vector v, and remember the components of this vector are 3, 1, and I have vector w whose components were negative 2, negative 1, right? Now, in order to find projection of v onto w, if you notice, by the way, w pointing totally different direction, v is going in the other direction. So in order to project v onto w, I extended w in this direction, okay, in the direction of v. So I can project v onto it. So if I drop from the tip of v, if I drop the perpendicular distance, it would be like this, that distance right there. The projection is actually this portion. There you go. That's going to be v1, if you will. V1 or horizontal. That's the horizontal projection, right? The horizontal component. And the vertical component is actually this one, right? This is V vertical. Again, in your book, the vertical component, he calls it V2, and the horizontal component is labeled as V1, just so you know. The horizontal is the projection. Okay, now I guess need to decide whether this VV, the vertical component, is going to go this way or that way, correct? Well, let's see. If I have two vectors again, this is vector V, and this is vector, let's say, vector that is in the horizontal direction, going in this way. Right? If I draw my vertical component like this, well, see, they cannot be tip to tip for me to add, because remember, the horizontal plus vertical component should equal to the vector itself. Well, this way they cannot add. So the only way V can be the sum of those is if I have a vector going in this direction, right? And now I can use the tail to tip method, right? Tail of one, tip of the other, to find the sum vector. And that's what V is. Therefore, the direction is like that on my Cartesian coordinate. So it's going to go in that direction. And if you look at the answer we got for the vertical component, it's 1/5, negative 2/5. So it's exactly this. It's like 1/5 here, negative 2/5 here is going to be here, right there. It's actually a position vector. So this is what the vertical component is. See that? There. That's precisely what this is. You see? And there we have it. So we just want to, again, the geometry of this really helps. Now, if you find the projection of V onto W, how is that going to be? Well, if I want to graph it, the projection of V onto W, I'm going to extend V, right, in this direction, and draw perpendicular from the terminal point of the vector. So the horizontal direction, there you go. That's going to be the projection of W now. I'm doing W onto V. W onto V. Okay, that's what this part is. And this piece right in here, right, that's going to be the, call it W2, right, the vertical component of the projection. This is W1, the horizontal component. So how am I going to find these? Well, let's do it real quick. Projection of V onto W is going to be V dot W. That part doesn't change because V dot W, W dot V is the same. Now we want V onto W. What did we just find? Oh, we did V onto W, right? Okay, let's do W onto V. Sorry. We're going to do projection of vector W onto V. So the numerator doesn't change. The denominator now, it's the one you're projecting onto, is the magnitude of that squared times in the direction of V. Okay, W in the direction, and this is the direction of V. Okay. So the dot product is -7. That's not going to change. Magnitude of vector V is 3 squared plus 1 squared, square root of that, and then we square it again because of the denominator is the square times vector V, which is 3, 1. And when you do this, you should get the denominator's square root of 10 squared, that's just 10. So I get -7/10 times 3, right? That's -21/10, comma, -7/10. All right, and there you have it. Notice we got a different result. Both components are negative, so that means the vector, the terminal point of the vector is in the third quadrant, as you can clearly see. That's where it's at, right there. Okay, -21/10 is 2.1, -2.1, and it's actually scaled pretty good on my graph. It's almost at -2.1. And what about the vertical component of the projection, W2? That's W minus the horizontal. Again, this is W vertical, which is W minus the horizontal component. And this is the horizontal component. Okay, and the vector W, that one was what, -2, -1. And then we're going to subtract -21/10 and -7/10, the horizontal component from it. And what do we get? We get -2. Negative and negative is positive, so that's 1/10. -1, negative is positive, so that's going to be -1 plus 7/10. So that's -3/10. And there we have that one. Okay. And again, this is as a position. Okay, this is a position vector, meaning if you want to graph this, you have to graph it on the coordinate system. X is positive, Y negative, so it's going to go like this. There you go. That's going to be the component of it. Okay, the vertical component of our projection. Perfect. So there you have it. Now, I still like to do some examples, a few more examples. So we're not doing bad. This is only 54 minutes. Now, let's take a look at a couple of examples and then we'll just wrap this thing up. Okay, so I'm going to grab a couple of examples, applications from the book, and then I will paste them here and we'll go from there. All right, so let's take a look at this example. The question reads, a Toyota Sienna with a gross weight of 5,300 pounds is parked on a street with an 8-degree grade. The grade is the slope of that hill, let's say, 8 degrees. See the figure. Find the magnitude of the force required to keep the Sienna from rolling down the hill. What's the magnitude of the force perpendicular to the hill? Okay, and in the drawing, the author has pretty much done this for us. Notice we have, this is the perpendicular and that's the horizontal component of the force. The force here is the weight, right? The force vector is the weight vector, the weight of the Sienna, 5,300 pounds. So what I've done on the right side is I've done a blow up of this smaller figure so we can kind of see that a little better. Now, if we look at this triangle, okay, this right triangle here, if you will look at just this one, this is a right angle. The measure of this angle is 8 degrees, right? And because it's a right triangle, then this other angle is complementary to 8 degrees. So the measure of this angle is actually 82 degrees, correct? Okay. So we have it for this triangle. Now let me remove that, but keep in mind that we've found the measure of this angle, this to be 82 degrees. Now, in terms of these two vectors, one that's going in the horizontal, let's call it a downhill force, this one, and this one is the perpendicular force, right? That's what those are. So I'm looking at those. These two are perpendicular to each other, right? The horizontal vertical components are perpendicular. That means this angle is a 90-degree angle, right? Well, if this angle is 90-degree angle, and we have already 82 degrees here, right? That's what that is. 82 degrees is in here. Then this other angle right in here, this angle, tiny angle, is 8 degrees, correct? To make up the right triangle. All right, or right angle. Now, what I want to do is actually, I'm going to draw the weight vector. That's 5,300 pound weight. And I'm going to draw those red vectors. This is the component of the force that is perpendicular, right, to the hill. That's this part. Call it FP. We established the measure of the angle is 8 degrees, the same as the grade for the street. And the horizontal component is actually this component, right? We're going to call that F. Call it the downhill force, right? FD. Now we can actually translate this vector into here and close the triangle, right? So we have a closed figure. So this is actually F force downhill. Okay, the force vector. Perfect. And we have created our triangle this way. Now let's write some basic stuff about this triangle. Remember, perpendicular horizontal components are orthogonal to each other. They form the right angle. Now, let's do sine of 8 degrees in this triangle. What is the sine of 8 degrees? Sine is the ratio of opposite. Side opposite is magnitude of the force downhill divided by the hypotenuse. The hypotenuse is the weight vector, which magnitude of it is 5,300, right? So if we cross multiply, we get magnitude of downhill force is going to be 5,300 sine 8 degrees. And once you do the computation, this number turns out to be about 737.6 pounds. Okay. And let's do cosine. Cosine of 8 degrees. Cosine of 8 degrees. Cosine is the ratio of adjacent to hypotenuse. So that's going to be the magnitude of This is the adjacent magnitude of the force that is perpendicular to the hill divided by 5300. And from this we can again cross multiply and get magnitude of perpendicular force is 5300 cosine of 8 degrees. And this number turns out to be 5,248.4 pounds. And that answers the question that the problem was asking for. Again, the problem said find the magnitude of the force required to keep Sienna from rolling down the hill. Well, the horizontal component is what's going to cause this to roll down, right? That's FD. This is for downhill force, right? That's the answer to the first part. And what is the magnitude of the force perpendicular to the hill, which we just found. All right, let's look at one last example and we are done with this lecture. Now for this next example, the question reads, Billy and Timmy are using a ramp to load furniture into a truck. While rolling a 250-pound piano up the ramp, they discovered that the truck is too full of other furniture for the piano to fit. Timmy holds the piano in place on the ramp while Billy repositions other items to make room for it in the truck. If the angle of inclination of the ramp is 20 degrees, how many pounds of force must Timmy exert to hold piano in position? Now remember, the piano has a tendency to roll down, right? If Timmy wasn't there, it would roll off the ramp. So in order for Timmy to hold piano in a static condition, the force downhill should be equal to the force that Timmy exerts, right? Exactly in the opposite direction, horizontal, both horizontal. So whatever this force is, it's got to be exactly the same force. So that will be the opposing force. We want to know what the force what force must Timmy exert. So that's what we want to find out. Now again, based on what we just did up here for inclined planes, the way the geometry of this works, it turns out that for that inclined plane, the angle is 20 degrees, right? That's the angle of inclination for the ramp, 20 degrees, correct? And this part is vertical. That's the weight of the piano, 250 pounds, right? And just like the Sienna example, we can actually draw these horizontal vertical components of this weight vector, which is our force vector now. There you go. So the part of it, again, you have two components of the force. One is perpendicular, the other component is, call it D again for downhill force. So the force Timmy exerts must equal to the force of the piano towards downhill. All right, and again, you can transfer that force, downhill force here. We just showed the measure of this angle will be the same as the angle of inclination. You can look up here the way I did the derivation of this one. It's exactly the same. Perfect. And then we can simply do a sine, right? If I do sine of 20 degrees, and we're looking at this triangle. Sine of 20 degrees is the ratio of opposite. Well, opposite is magnitude of the force downhill, which is the force, again, Timmy must exert on the piano, divided by hypotenuse is 250. Okay, and from this, the magnitude of the force downhill is equal to 250 times sine of 20 degrees. And this should give you about 85 and a half, not degrees, sorry, pounds. 85 and a half pounds. So that is the force. That is the force that Timmy must exert to hold the piano in position. The answer is 85.5 pounds. Okay. And I think we're good. Again, I'm trying to keep these videos to about an hour long, as if we are in a classroom. So, we are actually done with this lecture, and hopefully we're able to cover the dot products like we were supposed to. All right. Again, thank you for watching, everyone, and hope to have you in the next in my next lecture. Take care.